There we go. And even though it's not useful, I'm going to hand back labs while I'm recording because otherwise I'll forget to start again. There we go. So labs are going back. I think this block was good. Everybody, oh, congratulations. You guys all handed in your labs. My other block, there was like one person in each of them who didn't give me the lab to like so I could record the mark. But you guys did it. High fives all around. All right, so listen for your name. I will give you back your lab. The reason it's going to be nice is this weekend, one of the things you'll be doing is you'll be setting up, I was going to point to it, but I turned the thing off. You'll be setting up lab 12A, so it'll be nice to know what you need to do for that. Right? Yes? Oh, well, if you wanted to, if you go down below, there's round bottom glass down there, Florence glass. Somewhere. Or you can just leave it on the counter, which is what I've done with it so far. Okay, Hayden, your lab. Simon. Yura is not here. Abdullah. Noah. Oh, that's yours. Yubin. Yunda. There you go. Yunda Patrick. Ben. And Norman. Hui Yin. Go, Norman. And let's see, Rade's not here. I don't know. Matthew, Norvin, and then Oren, I think you're next. Yes, I have it right here. I swear I put it just right here. Oh, I did. There you go. And there's no answer. That's okay. We need to get you your lab back. You sure can. Yes. Huh? That's for you to keep. Yep. And if you need to hole punch it so it fits in your binder, there's a hole punch on the front table there. No problem. No problem. The homework will all be on Teams. Yeah. I'm recording this, so we're good. Yep. Did I put my phone into my purse or did I just put it somewhere random? No? No. Did I put it in my school bag? I did. Okay, good. I'm going to put it in my purse because that would be a better place for it. Because I could not find it last night. The battery was dead. And I realized when I had taken it home from school last time, for some reason I'd put it in this pocket here. Why I did that, I don't know. I never put it in this pocket, so it was as good as lost. Oh. There's a reason we still have a landline at my house. It's so I can phone my cell phone to find out where it is. I know there's like an app that will do it, but you know. They are, you don't need them today per se. If you are interested in working ahead over the weekend, there's 2.2C in the afternoon, but we won't get to it today. So I had high hopes, but then I realized I'm like, oh, I was crazy to think we'd ever get through that much in one day. Anywho, we are going to go back to 2.2b. This is 2.2b. And it's page 26. And I'm just going to erase this so we can review a little bit of what we did last day so that you remember. Okay. Okay, so we're going to remind ourselves, last day we were looking at this equilibrium, H2 plus I2 in equilibrium with 2HI. And when last we left, we had stressed the system by increasing the concentration of H2. What did that do to our forward rate? It increased our forward rate. So our forward rate had increased. What happened to our reverse rate? In that moment, what happened to the reverse rate? Nothing. Not yet. We're not at the shift yet. We're still in the stress, okay? So the forward rate was increased, the reverse rate was staying the same, and so now we have the forward rate being faster than the reverse rate because the forward rate sped up and the reverse rate stayed the same. And now we are shifting, and because our forward rate was faster, that means we're shifting to the right, which means we are making HI faster than we're using it up. And we are using up our H2 and I2 faster than we are making them. So the HI goes up and the other two go down. Are we remembering this? Excellent. Now, if the H2 and the I2 concentrations are now decreasing during the shift, what is going to happen to our forward rate? Remember, this is happening during the shift. Yeah, the forward rate is going to decrease because our concentration of H2 and our concentration of I2, those are both going down during the shift. And therefore, the forward rate decreases during the shift, which means that if we had our forward rate and our reverse rate that were initially equal, we added some H2 and our forward rate spiked. Yes, we got that vertical spike with our stress. And now during the shift, the forward rate is decreasing. What should that decrease look like? Should it be a straight line or should it be a curve? What should it be? It's a curve. And where does it end? It ends kind of in the middle. Yes? Because what's going to happen to our reverse rate? It's going to go up because the whole goal of shifting is to get back to equilibrium, which means that the rates need to be equal again. Yes? You would say that it is shifting to the right. Yeah, that's the language we would use around that. Okay? Yes? In concentrations, yes. In rate, no. So we're just going, other than qualitatively, we'll be like, oh, our forward rate and our reverse rate are now both faster than they were before, right? But only in a qualitative sense. Yeah. Sorry. Was that Eldon? Haven't seen him since grade 9. He looks like he's grown up. You know, it's weird, hey? Okay, so the new forward rate and the new reverse rate are both faster than their initial values. Okay, and during our shift, because our HI was increasing, and that meant our reverse rate was increasing, which we just drew there. That was our red line curving up to meet the reverse rate, or sorry, the forward rate in the middle there. So that's kind of where we left it last day. And now we're going to take a look at a concentration diagram of what is happening. All right, so instead of having rate on the y-axis, we are going to now have concentration on the y-axis. And once again, I will rewrite our equilibrium so we have it right in front of us. And the thing to realize about our initial concentrations is that you have to be told what they are. Okay, there's no way for you to know what the initial concentrations are unless I tell you. And because we are mainly concerned with what's happening during the stress and the shift, the initial concentrations are actually usually set arbitrarily. Do you guys know what it means for something to be set arbitrarily? It means randomly. So what it means is that I could say that this top line is the concentration of H2, second line is the concentration of I2, and the third line is the concentration of HI. And you can write those ones down if you want to. Those are ones that we're going to use. Don't write down the next bit. Or you could say that this, oh, why don't I make this one I2, and this one HI, and this one H2? Would that be okay? No, it'd be fine. It would be totally fine. You can set them, your initial values, wherever you want to. Okay? I could set this to being HI and this being H2 and this one being I2, and that would be okay. And I could set this to, I don't know, I2, HI, H. There's so many different ways I could organize it. Yes? It really doesn't matter. Where I put them is arbitrary. Don't write all those down because we need to now write actual things on our graph. Okay, so remember, what was our stress? Our stress was a increase in the concentration of H2. So we're going to draw that on our diagram here. Right at that point, we increased the concentration of H2. What does that look like on our graph? That's going to be a stress. That is our stress. So what does it look like? It's the spike. It happens in an instant. And which of these things are going to spike? Are all of them going to spike? Are some of them going to spike? Just the H2, because it's the only one that we changed. We increased the concentration of H2. Yes? There we go. We didn't change the other ones, so they just stay the same. Now that we've had our stress, now the equilibrium is going to shift. Which direction is it shifting? It is shifting to the right. What does that mean in terms of the concentration of H2 now? during the shift, the concentration of H2 will, yeah, it'll decrease. I can tell because there's a few ways of doing it, okay? The rate way of doing it, which is what we've looked at so far, is to say, I increased my concentration of H2, yes? What that meant is that my forward rate is faster than my reverse rate. And that means I'm using up H2 faster than I am making it. So the concentration, which was shot up, is now going to come back down. There's other ways of predicting the direction of the shift, but we'll get to that after we've done this page, okay? Because this is mainly rate focused right now. Now, the concentration comes back down. It never makes it back to its original value. So if I draw my original value line here, H2 is going to try to get back to where it once was, but it is not quite going to succeed. It's going to get close, but it doesn't quite succeed in getting back to its original value. It has to do with the math of the whole thing. And we will do the math later, okay? Right now we're doing it fairly qualitatively, but we will be doing it in terms of numbers later. Like this goes up by this much, so how much does it then change? So it gets close, but not quite back to its original value. Now, if my H2 decreased, what happened to my I2? Does it increase or does it decrease? Okay, if I'm using up H2, which we just said, yes? What's it reacting with? So what's happening to I2? Yeah, it's also getting used up. Yep, exactly. Okay, so our I2 also decreases. So during our shift, it's going to decrease. Does it decrease by the same amount or by a different amount? And how can you tell? What's my coefficient here? And what's my coefficient here? For every one hydrogen that reacts, one I2 also reacts. For every one H2 that reacts, one I2 also reacts. And if that's the case, if we said that H2, say for example, if we said it decreased by an amount we're going to call X, by how much would I2 decrease? It would also decrease by X. No, it doesn't have a spike because it did not get, we didn't change the I2 concentration. The system shifting is what's changing the I2 concentration now. Yeah? The system is going that way. So it's using up H2 and I2 in a slowish process. That's why it's a curve and not a straight up and down. And what's happening to the HI in the meantime? It has to be forming, yes, because we're using up H2 and I2, and we are making HI. So we're using these up, and we're making the HI. Are we making HI? Are we making the same amount of HI? Are we making X amount of HI? Yeah, we're making 2X because of that coefficient there. So during the shifts are always proportional to the coefficients. Yeah? So I'm going to have to kind of eyeball what 2X would look like and be like, okay, that's probably about like that maybe, right? And I'll be like, okay, I don't know if I did a really good job, so I'm going to label it as 2X. So hopefully that looks kind of like 2X. And yes, the lines can cross over each other. That's totally fine. Okay? Shifts are proportional to the coefficients of the equation. So for every one H2 that reacts, one I2 reacts, and 2 HI form. And that's why HI is going up twice as much as the H2 and the I2 are going down. So if that's the case, which direction has the system shifted? It has shifted to the right. Okay. Now on the next page, simply because it is the next page, we're going to repeat ourselves just so we have the information right in front of us. When we increased the H2, the system shifted to the right. Chat with your partner and decide, is there any other concentration change that we could make? And I don't know what happened to the grammar in this. So I'm just gonna do this. Is there any other concentration change we could make to get the system to shift to the right? There, that's better. I'm gonna have to fix that. Is there any other concentration we can make change to make that shift to the right? What else could we change? We could change the concentration of I2. What would we do to the concentration of I2? We would increase the concentration of I2. So if we increase the concentration of I2, we're going to draw a quick rate diagram and a quick concentration diagram showing what happens here. Both of them have time on the x-axis. In the rate diagram, of course, we need to have a forward and a reverse rate. It's good to label it, that way you know which one is which. I think I have one handout where the reverse one is like solid and the forward one is dashed, and it really bugs me because all the rest of them are backwards, but I've tried to redo it and it's a pain in the ass. So I'm like, do I really want to? I might do it over the weekend so you'll get a better one, but if I don't, I'm sorry. Would you rather I mark your tests or get those things switched? I'm going to mark the test, so if they don't get switched, you might just have to put up with a forward rate that's a dashed line. Okay? Okay. Something I will fix in the future. All right, so initially, before we've done the stress or anything, what is true of those two rates before we stress the system? They're equal. They're not both increasing. They're both just staying constant and equal. No, no, oh, when we increase the I2, then we get a change. But before we stress the system, so here is going to be our stress, which is an increase in the concentration of I2. What happens to our forward rate? It's going to go up. Spike. Forward rat increases. Excellent. Always like a good rat increase. What happens to our reverse rate in that same instance? Nothing. It just does nothing. It just hangs out here and waits for the shift. Yep. And now, after we have our stress, what happens? Now we get our shift. Yes? And during the shift, what's going to happen to our forward rate? Forward rate is going to decrease. What's going to happen to our reverse rate? It's going to increase until what? Until they meet in the middle and are equal again. Oh, that's a terrible line. What happened there? That looks like an S curve. Oh. Uh-oh. There we go. There. Fixed it. Okay. Until the rates are equal again. Now we're going to do our concentration diagram, and just to mix things up, what did I do with my other block? Which one did I put where? Okay. I put HI at the top. Let's put HI at the top. Let's put H2 here, and let's put I2 here, just for fun. All right, we increase the concentration of I2. What does that look like? It looks like a spike. Who spikes? I2. And it doesn't really matter how much it spikes. I generally just tend to not make it go past the other one because otherwise it gets confusing. Yeah? Now, after our stress, which way will the equilibrium shift? To the right. So what are we doing with H2 and I2? We are using them up as we shift to the right, and we are making HI. So I2 is going to go down. Where does it get to? Does it get to line A? Does it get to line B? Or does it get to, don't draw this, does it get to line C? A, because it doesn't quite make it back to where its original value was. Okay? Pardon me? At least for a concentration stress, yes. It's going to be different when we have different types of stresses, like a pressure shift and a temperature shift or stress, pressure stress and a temperature stress, but we won't get to those today. Okay, so there's our I2. What does H2 do? It's going to spike? It's going to shift without a spike. Yes, it is. It's going to shift without a spike. So it is going to, is it going to shift up or down? Down. Same amount as I2 or different amount? Why different? Same, because the coefficients are the same. Yes. And I'm sorry my curves look dreadful. They're just like they're just there. They keep trying to be S curves, and that makes me sad. All right, now how about HI? What happens to HI? It increases, and I did not draw this very nicely because I wrote things there, and this has to increase by how much? 2 times as much. So I'm gonna like, whoa, right? Like it's almost off my graph here. So maybe I didn't choose a good place to put those. Don't worry, on my quizzes, they're all in nice places, so it won't be weird. Yes? How much? Yes, so because this has a coefficient of 2, it goes up by 2 times as much, whereas these ones only go down by 1 factor. And if you label it, you're good. Yeah, I tend to label it because sometimes my 1x and my 2x look the same. You know what I mean? The distances are not really great. Yeah. Yes? Huh? Huh? Oh, there is no reverse. It's not a forward and reverse. It's just what's happening to the concentration. The concentration of H2 goes down. There's nothing, it doesn't split into 2 and half of it goes up and half of it goes down. I don't know, am I answering your question? Okay, yes. Yes. I mean, even if you had something that looked like this, you're like, okay, this is X, and this is X, and this is 2X, and obviously these two look like the same size, but if you've labeled it correctly, it's okay, right? You know, it just makes life easier so you don't have to worry too much about how good of an artist you are, okay? And actually the nice thing about the X and the 2X, when we start doing the math, we're going to be using those X's and 2X's. Yeah? And we're going to be solving for X. Oh no, it's easy. It's easy. It's easy algebra. Okay? It's not, no, it's easy algebra. It's like grade 8 algebra. Yeah, very much so. I mean, the worst thing you're going to have to do is take a square root, right? Like, it's not like pre-cal anything. It's like, no, it's just nice, straightforward math. Okay, it's math that makes me happy, so, you know. All right, is there another thing we could do to our system other than increasing? We increased H2 to make it shift to the right, or we could increase I2 to make it shift to the right. We could decrease the HI. Yes, we could. Is this like physics, Simon? No, I didn't think so. But does it make sense kind of in the same way? Yeah. Yeah, exactly. Yeah, it's similar, but not really. Yeah. Yeah. Okay, we can decrease I2 to shift the equilibrium to the right. So if we decrease HI, our stress is a decrease in HI. What happens to our forward rate? Why? Hold on. What concentrations affect my forward rate? Have I done anything to my H2 and my I2? Of what? Forward rate will increase. Why? Oh, but we're still just in the stress, right? We're in that instant. We haven't shifted at all yet. In that instant, what happens to the forward rate? Nothing, right? Because we have not changed the concentration of H2 or I2 in that instant. Okay, so yeah. So our forward rate is unchanged. But our reverse rate, what happens to the reverse rate? That one's going to decrease because we've got a smaller amount of HI now. Whoops, what am I writing? Yeah. Yeah. So here we have our forward reaction and our forward rate, sorry, and our reverse rate. And initially the two are equal because we have a system at equilibrium. Rate diagram, so I got to label rate and time. And then right here, we're going to decrease our concentration of HI. So the forward rate remains unchanged because we didn't mess with the concentrations of H2 and I2. But what happens to our reverse rate? It goes down. So we see a spike, but the spike is now downward. Now, if our forward rate remained unchanged, but our reverse rate decreased, which rate is faster? If my forward rate is unchanged and my reverse rate, so here's my original ones, yes? So my forward rate is unchanged, but my reverse rate gets slower. Which rate is faster? Forward, okay? Yeah. And that makes sense if you look on your diagram. Where's the forward rate? It's up here. Where's the reverse rate? It's down here. Yes? What are those two rates going to do? So the reverse is going to go like up here. There's no x's when it comes to rates. The rates just try to meet in the middle. So this one's going to go up to about our midpoint. And the forward rate's going to go down to about our midpoint. What's really happening is that as the shift is occurring, our concentration of H2 and I2 decrease. Yes? Because we're using them up faster than we're making them. And as those decrease in concentration, what that means is our forward rate also decreases. And that's what's happening here. Yes? As the shift occurs, that was the first thing. The second thing is we are making HI, 2HI faster than we are using it up. So we are increasing the concentration of HI. HI is getting bigger. And therefore the reverse rate is going to get faster. Yeah. So we are making, HI initially got slower, right? That's why this arrow here is small. Yes? But now we are making HI faster than we are using it up. So what's going to happen at that point is now during the shift, so this is as the shift occurs, HI is going back up. And now because we've got more HI, there's going to be more collisions between HI. And what that means is our reverse rate is increasing. That makes sense? Yeah. Honestly, at some point, you get past the point of thinking about it in terms of rates. The rates is why it really works. But at some point, you're going to be like, okay, I have an increase, that means it shifts this way. I have a decrease, that means it shifts that way. Right? So, yeah. Okay, so that was our rate diagram, and that should be a nice sharp curve there. Now we're going to do our concentration diagram. God, are we not done yet? No, we're not. Okay, concentration and time. H2, I2, 2HI. We decrease our concentration of I2. How about I put I2 up here this time? I2, H2, HI. Because remember, those initial concentrations are arbitrary. They are set randomly, okay? The initial concentrations. Okay, at random. Okay, so we've got those, and now we stress our system. Well, why did I put an arrow there? That was weird. Okay, so now we're going to decrease our concentration of HI, yes? So right here, we decrease the concentration of HI. What does our stress look like on the graph? A spike for who? HI. Which direction? Down. Boom. Which way does the equilibrium shift? To the right. Which means we're now going to be making more HI, yes? So it's going to come back up. Does it get to its original height? No. Okay, so it's slightly lower than that original value. What will H2 do? It's going to decrease by how much? 2x or half x? If this is x, that's going to be a half x, yeah. Yep. What's I2 going to do? Decrease by half x, yes. And you see why I warned you use a ruler on a test, because I can't make my lines straight. Like, it's just hard. Okay? Now, rather than having to think your way through rates all the time, which is exhausting, yes? We're going to learn some general rules of thumb, okay? So in general, if we increase the concentration of a substance, if that is our stress, does the system shift towards that increase or away from the increase? So consider if we had A in equilibrium with B. If I increase A, it shifts away from A, yes? And you know what's nice about increase and away? They both start with vowels. So if you're like, okay, I'm having like a little brain fart on the test, this thinking through the rates thing is not cutting it for me, I can't even remember what it is. Oh, but increase and away both start with vowels. So if I increase a concentration, the system shifts away from that increase. And if we decrease the concentration, if that is our stress, then it shifts towards that increase, and decrease and towards both start with consonants. Oh, that looks like an I now. Okay, so again, if we had A in equilibrium with B and we had a decrease here, that would cause it to shift towards. Did you guys read about LeChatelier's principle? Did not. I've given it as homework twice now. Okay. Fair enough, you're honest, Rod, I appreciate that. Okay, so LeChatelier's principle says that if a system, this is Monsieur Henri Louis LeChatelier, the Americans pronounce it LeChatelier, and we Canadians all laugh at them because we at least had, you know, some grade school French. But regardless, he said, if a system at equilibrium is subjected to a stress, the system will shift in order to minimize that stress. So in Hebden, he's got this little thing where he's got a definition very much like this in a box, yes? And it says, this is the definition. And then down below it, it says you can think of LeChatelier's principle as being like, whatever we do to the system, remember what we do is the stress. Whatever we do, the stress, nature tries to undo. And so the shift is trying to undo the stress. However, do not, and Hebden says this in his book, do not use that if you're asked to define LeChatelier's principle. Do not say what nature does, what we do, nature tries to undo. But it's a good way of thinking about it. Like, it makes it easy. It's like, oh, I increased the concentration of A, so nature's going to try to decrease it by using it up. Yes? If I decrease the concentration of A, nature is going to try and make more A, right? In order to minimize that stress. So you have some tools at your disposal. You now know that a system shifts away from an increase and towards a decrease in concentration. You can just continue to use that and ignore what I'm going to say next. I really like this, so I'm going to share it with you. This is how I got through it. I'm a very visual person. I have like molecules in my head are all moving around. I have arrows. I see like the equilibrium moving. Like in my head, I've got this rope that goes like this. If this goes down, this goes up and over. If this goes down, this goes up and over. If this goes up, this goes across. But anyway, what you do if you want to use the head to tail method, if I were to increase the concentration of H2, and if I draw a line over top of the equilibrium arrow, making sure that's underneath, then I have to put the head of that arrow not touching the head of the other arrow. So my arrowhead is going to go here. It's very much like vectors if you've done vectors in physics. Oh, but this isn't vectors. It's just make it the tail touch the head. Yes? This isn't a vector. The tail to head thing just works the same way. So if I were to decrease, say, the concentration of HI, and I drew a line over top of that, which end should I put the arrowhead on? Because I want the tail to meet the head. Now, can you imagine if I was to draw it like this? Here, we'll get rid of this, and we're going to say this one is not. What if I drew my line and I put my arrowhead over here? What two things are touching? This arrow's tail and this arrow's tail. So tail to tail is a no-no. And if I were to put my arrow here, the head would be to the head. So you can't have two heads touching, you can't have two tails touching. You have to have a head touching the tail and a head touching the tail. The other thing you have to make sure is that your horizontal line is at the top. Your horizontal line has to go at the top. It cannot go at the bottom. Okay, otherwise it doesn't work. The horizontal line must go at the top of the vertical arrow. I always feel like when I teach this, like I'm just like humoring myself, because nobody looks at it and goes, my God, that is beautiful in its simplicity, which I think it is. It's like, imagine you have a rope, yes? And if I push up on this end in order that it doesn't go slack, this end has to go that way, yes? And if this goes up, which way is this part of the rope going? It's going across that way. Wah! Yes? So if I increase something, we go this way. And if I decrease something, which way does the rope go? It goes that way. Yeah, you guys give me the same reaction as everyone else. You're like, yeah, whatever. It's so not confusing. It would go up, goes away, down. Whew. Right? Because if I had a rope that went across this whole thing, okay, so it went like this. If this part of the rope was going up, then this part of the rope would have to go that way, and this part of the rope would be going, yeah. Okay, never mind. Okay, moving right along. Explaining shifts in terms of LeChatelier's principle versus explaining it in terms of rates. You need to be able to do both. Explaining in terms of rates is a pain in the butt, but you need to be able to do it. So here we have a system. Consider the following system: 2NO plus H2 in equilibrium with N2O and H2O. In which direction does the equilibrium shift when some NO is added to the system? Does it shift to the left or does it shift to the right? I've increased my concentration of NO, therefore it shifts to the right. How do we explain this in terms of LeChatelier? Well, the first thing you want to do is you want to talk about the stress. And you're going to tell me what the stress was. The stress was an increase in NO. Then you're going to talk about the shift. The stress was an increase in NO. Therefore, the system shifts to the right. And because this is LeChatelier, you're going to talk about what nature is trying to undo, right? So you're going to say we had an increase in NO, so the system is going to shift in order to use up NO and bring the NO concentration back down. So we made the concentration go up. The system is going to shift to use up NO to bring it back down. Yes? Sure. We just haven't looked at that yet. We will be in a moment though, okay? When NO is added to the system, explain the shift in terms of rates. Now this is much more complicated, but we still need to be able to do it. I know it's Friday afternoon. Try and pay attention if you can. Smack yourself on the cheek. Just do that. Okay, here we go. Here we go. We can do it. We can do it. Okay? If I can be up here teaching at the end of the day, you can pay attention for another couple minutes. If you need to stand up, whatever makes it easier for you. N2O plus H2O. Okay? When we increase the NO, what happens to the forward rate? The forward rate increases due to an increase in the number of collisions between reactant particles. That's our NO and our H2. So when you're explaining in terms of rates, you're going to say what happens to the rate? What happens to the forward rate? What happens to the reverse rate? Hold on, in that moment, the reverse rate stays the same. Because the concentration of the products, have they changed? Nope, I only see one arrow there. I have not changed the concentration of the products. The concentration of the products have not changed. And it's at this point that I very often like to say my forward rate increased, so I'm going to draw a big arrow going that way. And my reverse rate stayed the same, so I'm going to draw a smaller arrow going backwards. Because that's going to allow me to easily say that which rate is faster than the what rate? The forward rate is faster than the reverse rate. If our forward rate is faster than our reverse rate, which one are we making faster than we are using them up? Reactants or products? We are making products faster than we are using them up, which means the system shifts to the Product, which is on the right. We have one more example to get through, and then we're done, okay? In which direction does the equilibrium shift when we remove some H2 from the system? So I'm just going to write it again here. We had H2 plus 2NO in equilibrium with N2O plus H2O. What if I remove some H2 from the system? The system's going to shift to the left. So we're going to say that the first thing we mention is the stress. The stress to the system was a decrease in H2. The next thing we mention for LeChatelier is that the system shifts, and we say which direction it shifts to the left. And remember, this is all about doing and undoing. So what did we do? We decreased the H2. So this is going to be in order to make more H2 to bring the concentration of H2 back up. So that's LeChatelier. Rate explanation. Oh, hate doing this at the end of the day, but that's okay. We're going to do it quickly. I made some typos. This is supposed to be H2. Okay, we're going to stay for 1 minute because we need to finish this. I'm sorry. When the H2 is decreased, what happens to the forward rate? Hold on. Yes, you're right. It decreases. Because there are fewer collisions between reactant particles. Now we're just going to cross out this because I was thinking backwards somehow. What happens to our reverse rate when we decrease the concentration of H2? What did I do to my product concentrations? I did nothing to them. There's only one arrow here. I did nothing to those concentrations. So what happens to my reverse rate? It stays the same. So the reverse rate stays the same because we did not change the product concentrations. So once again, here's where I put my arrows. My forward rate got smaller, but my reverse rate stayed the same. So which rate is faster than the other? So the reverse rate is faster than the forward rate. So which one are we making faster than we are using it up? We're making more reactants, so we're making reactants faster than we are using them up, and therefore the system is shifting to the left. Okay, so your homework, it's all going to be on the Teams. Set up 12A. You're going to have to go on there for changes to the equipment. And do this worksheet. Do this worksheet. 12A is a really long lab. Don't leave it to the last minute, okay? You'll cry. It's got 5 parts to it. We're doing it on Wednesday, but I will be signing it on Tuesday. Thursday, whatever, it doesn't matter. I don't know, that middle of the week day that's long. Yeah, whatever it is. So look on Teams for changes to equipment and materials and procedure and stuff. And have a good Thanksgiving. And if you make pumpkin pie, use orange juice concentrate because it makes it way better. Wow. You too. Take care.
I put that because that was the only one that made sense. Like it decreases the because it's like the worst bad death. So I put that was like it was a partial guess because I didn't actually understand more. Yeah.
You too. Bye.